our next section is 3.6, which is rational functions. A definition of a rational function to start. We have worked with these expressions quite a bit this quarter already. What's going to be brand new is really getting into the details of the graph and the important values of a rational function. A rational function is of the form r of x equals p of x over q of x, where p and q are polynomials. To simplify things a little bit, we'll assume p and q have no factor in common, which would just mean that that rational expression is simplified. There's no factor we can cancel out. We'll address a little bit through some homework what might happen if there is a common factor. Even though rational functions are constructed from polynomials, their graphs look significantly different than those of polynomial functions. We'll still find intercepts and look at some important values that way, but the graph looks different. Recall that to determine the domain of a rational function, we have to look at the zeros of the denominator. We would exclude those values from our domain. We want to graph rational functions. So let's start with what's probably our simplest rational function, f of x equals 1 over x. One interesting thing to note is that the domain excludes 0. So in thinking about the graph of this, we might ask what really is happening near 0. Is it just a hole at 0? Does it jump over 0? What's going on? Here are a couple of tables that look at what's happening to our function values near 0. So there's a little new notation here. This 0 with a negative on our superscript means it's approaching from the left. So you'll see all these values are really tiny numbers that are close to 0 on the left, slightly smaller than 0. Over here with that plus sign from the right. So here we're just exploring if we're really close and getting closer and closer to 0 on the right, or just greater than 0, what's happening to our y values. And you can see in both of these cases, the y values are getting big, in this case really big negative, in this case really big positive. We could write, let me use notation that we're familiar with for end behavior. We could write something like as x approaches, using this kind of notation, 0 from the left, f of x approaches, well that's this one, negative infinity. We could also say as x approaches 0 from the right, that's a superscript, that's a plus. Our f of x values, well, it appears they approach infinity. So this should be familiar notation from end behavior of polynomials. But we're not looking at the end, we're looking at what's happening right at 0, just using similar notation to describe it. Okay, so that's kind of interesting. If we think about what our graph looks like, just briefly, well, coming into 0 from the left, our values are heading down to negative infinity. They get really close to the y-axis where x is 0. But don't ever cross it, just keep getting really big negative. And on the other side, getting really big positive as we get closer and closer to x equals 0 from the right. Okay, so then we might wonder, well, what's going on at the ends? And certainly we can make a table of values and plug in some points to get a little more precise here. But if we want to look at in general at what's happening on the ends, or the end behavior of f, we might consider a table in the same way. If we look at the very end on the left as x approaches negative infinity, so getting bigger and bigger here, it looks like our y values get teeny tiny, close to 0, from the bottom. And if we look at what happens as our x values get really huge, approaching positive infinity, well, again, we're approaching 0. So using that same notation for our end behavior, we could write as x goes to negative infinity, the f of x values go to 0. And as x goes to positive infinity, the values of f of x go also to 0. Using this information, and also maybe just plot a few other points. If I plug in 1, I get 1 over 1, or 1. If I plug in -1, I get -1. We could find a few more points, but here's what the graph of f of x looks like. So we can see all of that behavior that we just described. Getting close to 0 on either side, it's either going to positive infinity or negative infinity for y values. As x goes to negative infinity, f of x goes to 0, and as x goes to positive infinity, f of x goes to 0. We've actually seen the graph of 1 over x before. We haven't looked at it in a little while, but I wanted to really zone in on these important spots. Let me give you some vocabulary to help us describe this end behavior and this middle behavior, this idea of heading off towards infinity. The line x equals 0, which is just our vertical axis. Here's the line x equals 0, vertical line. This line x equals 0 is called a vertical asymptote of the graph. The line y equals 0, which is this horizontal line that in this case is just our x-axis, is called a horizontal asymptote. Informally speaking, an asymptote of a function is a line to which the graph of the function gets closer and closer as one travels along that line. Here's a more formal definition. The line x equals a is a vertical asymptote, so x equals a would be a vertical line wherever that line a is. Here are 4 different examples of vertical asymptotes. It's a vertical asymptote of y equals f of x if y approaches either positive infinity or negative infinity as x approaches a from the right or the left. So this has gotten kind of tiny. I don't know if you can see there's a superscript of a plus and a minus, a plus here, a minus here, just like we talked about. If any of these 4 situations happen either on the right or the left, we've got a vertical asymptote. The line y equals b is a horizontal asymptote of the function y equals f of x if the y values get close to b as x approaches either positive or negative infinity. A rational function, well, we've seen it with one example. A rational function has vertical asymptotes where the function is undefined, that is, where the denominator is 0. So again, if you think of the function 1 over x, it wasn't defined at x equals 0. There was actually a vertical asymptote there. We have a little more work to do to think about how we find those horizontal asymptotes, and we'll justify this a little bit more. Let's start thinking about graphing rational functions. Some rational functions are just transformations of the function we just graphed. So for example, if we wanted to graph r of x equals 2 over x minus 3 using transformations, well, if we break that down, I'm seeing a shift to the right 3 here, and this would be a stretch vertically by a factor of 2 compared to the graph of 1 over x. All right, yeah, the graph of r is obtained by shifting 3 units to the right and stretching vertically by a factor of 2. We also might note, well, if we shift to the right 3, that's going to make our vertical asymptote x equals 3. But that shift and that stretch away from the x-axis, neither are going to change our horizontal asymptote of y equals 0. Here's a graph of 2 over x minus 3 equals r of x. Vertical asymptote, horizontal asymptote. It's stretched a bit, but similar in shape to the graph of 1 over x. Well, that's nice, but what if it's not just a simple transformation? A rational function is any polynomial over polynomial. So how would we graph something like this function, r of x? Certainly, as we're discovering, one important feature of rational functions is asymptotes. And let's look more carefully at how we might calculate those rational functions given an equation. Here's an example. I've already given you the vertical and horizontal asymptotes. If we want to verify that information, we can kind of see here a horizontal asymptote of y equals 0 because at the ends our graph is getting close to 0. That's our horizontal asymptote. And I can also see vertical asymptotes. If I draw on the vertical line x equals negative 1 and x equals 2 here, I can see that my graph either goes to positive or negative infinity on either side of these vertical lines. So these are my vertical asymptotes. This is my horizontal asymptote. Let me give you some ideas about how we might find those just given the equation. We already saw with the graph of 1 over x that the vertical asymptote came from the zeros of the denominator, that value where our function was undefined. I think that might be the case here too. If we were to factor this denominator, it factors into x minus 2, x plus 1. The zeros of the denominator, or the values we end up having to exclude from our domain, correspond to these vertical asymptotes. Our horizontal asymptote, well, let's think about that a little bit more. Our horizontal asymptote is a description of the end behavior, and if you remember with polynomials, the end behavior was based on the behavior of the highest degree term. If we take a look at our rational function, it's made up of two polynomials. The polynomial in the numerator has a leading term of x, and the polynomial in the denominator has a leading term of x squared. I would expect if the leading term determines the end behavior of the polynomial, probably this ratio of leading terms can determine the end behavior of my rational function. If I think about x over x squared for a minute, well, if I pull out a factor of x, that's equivalent to 1 over x, at least everywhere except at 0, because it's not defined at 0. But I'm worried about the ends right now anyway, not at 0. And I know that 1 over x, well, as x gets big, this goes to 0. We just looked at that. If this denominator gets huge, 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 either positive or negative, this fraction is going to get tiny. That idea of looking at the ratio of leading terms is what gives me my horizontal asymptote of y equals 0. I want to look at another example. Before we do, let me just make a comment about notation. Asymptotes are lines. So show an equation of a line when you write what an asymptote is. So for example, I wouldn't want to say the vertical asymptotes are -1 and 2. I'd want to say the vertical asymptotes are x equals -1. That's the entire vertical line as an equation, and x equals 2. Also, it's not correct to say the horizontal asymptote is 0. What's correct is to say it's the equation y equals 0. Let's see if we can apply these methods of finding vertical asymptotes in another example. Here's the function r of x is x squared minus 8 over x minus 3. The vertical asymptote is x equals 3. I can see that here in the graph. There's the line x equals 3, and that is most definitely the 0 of the denominator. It doesn't appear this has a horizontal asymptote. It appears maybe there's a line that it goes to at the end, but it's not a horizontal line. We will address what this type of asymptote is. There is some interesting long-term behavior here, but it's not a horizontal asymptote. How could I see that from the equation? Well, remember we said to look at the ratio of leading terms. The polynomial on top is dominated by x squared, and on bottom it's dominated by x. If I just look at simplifying this, it's the line y equals x. It doesn't go to a particular number. It goes to an entire other line that's not a horizontal line. So because I didn't just get a number, I would conclude that this doesn't have a horizontal asymptote. Let's think about this with one more example. The vertical asymptote here is x equals 3, and I can see that vertical line here. A horizontal asymptote of x equals 2, if I draw that line in, y equals 2. If I draw that line in, I can see my ends begin to match up towards that line y equals 2. Vertical asymptote is, again, the zeros of the denominator. Yeah, if I grab the zeros from this factor, it's x equals 3. My horizontal asymptote, I want to think of the ratio of leading terms. In my numerator, my leading term is 8x squared. And in my denominator, well, if I were to multiply this out, I would get a leading term of 4x squared. If I reduce this, 8 divided by 4 is just 2. So that gives me my horizontal asymptote of y equals 2. One last example. This has two vertical asymptotes from the two zeros of my denominator. That's here at x equals -3 and over here at x equals 2. That looks good. And my horizontal asymptote is y equals 1. On top, I'm going to have x cubed as my leading term once I multiply all this out. Again, I don't have to actually multiply it out to see it, but I would get an x cubed. And down in the bottom, I'd also get an x cubed. This is equivalent to 1. That gives me my horizontal asymptote of y equals 1. Here's a bit of a summary of this. I find this language a bit intense. I think it's easier to just think through what we were doing. But officially, if I've got a rational function, the vertical asymptotes are the lines x equals a, where a is 0 of the denominator. And our horizontal asymptotes, well, it might be 0. It might just be the quotient of the coefficients of the leading terms. If the degree on top is bigger, we don't have a horizontal asymptote. I would say, oh, actually, I wanted to say leading term here, not leading coefficient. Term. We just want to analyze the long run behavior of the leading term in the numerator over the leading term of the denominator. Sometimes it's the ratio of coefficients. That's if the terms have the same degree. But otherwise, just look at that ratio of leading terms and use those to determine the long run behavior. Let's try that with this example. Let's find the vertical and horizontal asymptotes of this rational function. So to find our vertical asymptotes, I want to look at the zeros of the denominator. So let me just grab the denominator. It looks like we might be able to factor this. Hopefully we can. Minus 3 plus 2 should do it. That means x equals 3 and x equals negative 2 are our vertical asymptotes. Again, I'm not just going to say the vertical asymptotes are 3 and negative 2. I'm going to write out the equations. X equals 3, x equals negative 2. Our horizontal asymptote, I want to find by looking at the ratio of leading terms. 5x squared over x squared. Well, since I have the same degree, I can just consider my lead coefficients. This reduces to 5. That means y equals 5 is a horizontal asymptote of this rational function. Here's what a graph of that looks like. We can see at x equals negative 2 and x equals 3, 2 vertical asymptotes, and y equals 5 is a horizontal asymptote. This one's for you. Find the vertical and horizontal asymptotes of the rational function. Post these in the conversation discussion for homework 6. We're going to look more generally at graphing rational functions now that we have an idea about how to find asymptotes. Here's a good set of guidelines to follow to determine the entire graph without just making a huge table of values or doing a lot of extra work. In general, we'll factor, because those factors are important for finding asymptotes as well as intercepts. So we'll factor and then find the x and y intercepts. They should be some easy values to calculate and really give us some direction about what our graph looks like. Then we'll find vertical and horizontal asymptotes. When we think about vertical asymptotes, we'll also want to maybe use some test values. Think about what the behavior is on each side of the asymptote. Does it go to positive infinity? Does it go to negative infinity? And then we'll use that information to sketch a graph. We can certainly make a table of values of some other points as needed, but we will have most of the important information in steps 1 through 4. Let's try it. Find the asymptotes and intercepts and sketch a graph. Okay, let's find our intercepts first. I'm going to start with the y-intercept. It's often the easiest thing to find. I can find a y-intercept by letting x be 0, so I'm going to plug in 0 into this equation. 4 minus 4 times 0 over 0 minus 2. That's 4 over negative 2, or negative 2. 0, negative 2 is my y-intercept. I suppose I should, technically my first step listed above was to factor this, so let me do that also. My x-intercept is where my graph, where my equation is equal to 0. And let me just remind you, a fraction is equal to 0 whenever the numerator is equal to 0. So in fact, I only really need to look at the zeros of the numerator in order to find the x-intercept. Well, if I want to look at this in the factored form, that might be even easier. That's going to give me an x value of 1. So I've got just one x-intercept at 1, 0. Let me just circle our important information here. We've got our intercepts. Let's try to find asymptotes. Our vertical asymptotes, remember, are the zeros of the denominator. So right away I can see I've got a vertical asymptote of x equals 2. Our horizontal asymptote depends on the leading terms. So in this case, negative 4x and x are our lead terms. If we look at the quotient of our leading terms, well, the degree is the same, so I can take out my x's. I'm left with negative 4 y equals -4 is my horizontal asymptote. Let's make some room to draw a graph. I've brought all of our information forward from the previous slide. I've got a couple points to plot, 0, -2, and 1, 0. I'll label these in order to indicate a scale. I also have a couple of asymptotes at x equals 2. I'm going to plot this with a dashed line. It's not part of the graph, so I don't want to fill it in with a line, but I do want to be able to show that the graph gets really close to this line from either direction. So sketching it in is worthwhile. At -4 down here, I can draw the line, y equals -4. Ideally, this is a little more horizontal, but this gives me my horizontal asymptote. Let's see what we can sketch with just the values that we have, and as needed we can put in some more test points. I know that my graph has to start really close to y equals -4, so I'm going to start out here really close to this line and come through my vertical intercept, 0, -2, and then I also need to come up and pass through the point 1, 0. What I don't know as I approach 2 from the left is whether my graph goes off to positive infinity or turns around and goes down to negative infinity. There are a few ways I could do this. One efficient way of thinking about this is to just try out some test points. If I look at f of x, well, if I were to plug in something really close to 2 on the left, like even 1.99, very close, I just need to determine, is the result positive or negative? I don't even have to calculate the exact value, although I could. If it's positive, we're going to positive infinity. If it's negative, down to negative infinity. So just thinking about this, if I plug 1.999 in here, or 1.99, 1 minus 1.99 is going to be negative. So that's going to give me a negative numerator, and 1.99 is going to give me also a negative denominator. A negative divided by a negative is positive. That's enough information for me to draw this in my graph. It heads off towards positive infinity. It can't be positive and then turn around to be negative and head towards negative infinity, because that would create another intercept here, which we know we don't have. All right. On the other side, I don't really have any points. It could either be this type of graph, or I think it could come up from the bottom and get close to y equals -4. Let's just go ahead and find another value. How about what's happening at 3? Let's plug in 3. If I plug in 3, 4 minus 4 times 3 over 3 minus 2 is -8. So let's just put the point 3, -8 in here. This is really going to be enough for me to say, yep, this is the behavior of my graph. I know that it can't head towards positive infinity up here, because if it goes through this point, it would have to create another x-intercept, and I know that's not happening. So this looks good for a graph of f of x. We need to practice this some more, so let's just do another one. Find the asymptotes and intercepts and sketch a graph. Let's start with a y-intercept. If I plug 0 in, I'm going to have, well, 0 plus 2, 0 minus 3, 0 plus 1 squared, and 0 minus 2. So this is going to be -6 over -2, or 3. 0, 3 is my y-intercept. My x-intercept is going to be 0 equals the entire equation. And as we said in the previous example, that really just means, as long as it's reduced here, that the numerator is 0. So this gives me two x-intercepts at -2, 0, and 3, 0. My vertical asymptote, well, comes from the zeros of the denominator. So I've got two of them, x equals -1 and x equals 2. Remember, these are equations of lines, so I need x equals. My horizontal asymptote comes from the ratio of the leading terms. On the numerator, I'm going to have a leading term of x squared if I were to multiply that out, and in my denominator, x cubed. If I reduce this behavior is like 1 over x in the long run, which means at either end it's heading to 0. So my horizontal asymptote is y equals 0. Let's see if I have enough room to plot this right over here. I know I have the point 0, 3. Again, I'll write in the point in order to indicate a scale. The point -2, 0, and 3, 0. Two vertical asymptotes at x equals -1. So let me put this in with a dashed line and label it. And x equals 2. And then a horizontal asymptote, which is just my x-axis. Note that the horizontal asymptote is really only giving us information about the end behavior. It doesn't matter if our graph crosses the horizontal asymptote in the middle of the graph. We really don't even need it in the middle of the graph. It is only an indicator of the end behavior. All right. It looks like over here we have to pass through 2, 0, but I could either come down through it and come back here, or maybe I could come up through it and then towards this. It looks like it might help if I had another test value here. Let me clear some space. I know that I have to come in really close to my x-axis, and then I have to pass through the line, the point -2, 0. It might help to have a value, one more value here, so that I know if I want to come down towards that, or if I want to come towards -2, 0 from above or from below. So I could make a table of values over here with some test points. Say I plug in -3. That's going to give me about -3/10, or exactly -3/10. So that tells me that I am below this line. So something like this coming from below. To determine what's happening at this asymptote, I just want to know, does it come up this way or does it bounce off and turn around and come down? If I were to calculate f of -1.5, say, if it's positive, I know I want to keep going up. If it's negative, I'll turn around here. So if I plug in -1.5, I get a positive value, 2.57. So I'm going to head up towards infinity here. All right, on my other side, I don't know, well, I think I can figure this out without any other test values. I don't know if it comes from negative infinity or positive infinity at this asymptote, but if it did negative infinity, that would create another asymptote, or intercept, which I don't have. Same thing over here at this asymptote. If I came down from my vertical intercept, I'd create a new intercept, which I don't have. So I think this just has to go something like this. To the right, well, I could plug in again something like 2.5. If it was up here, I know I'd have to keep going, because if it went up and came back down, I'd create another intercept I don't have. So let's look at one more test value. If I plug in 2.5, I get out something negative. It's about -0.37. And so that tells me this has to go down this way, and probably something like this. All right, I could calculate if I plugged in something just bigger than 3, I do get something positive, so it does pass through here and come back down. So this isn't the most beautiful graph, but it is a fairly accurate one with very little information of this function f. Let's do this again. Let's go ahead and factor this because these are not factored as is. Let's start with y-intercepts. F of 0 is, well, probably easier in the multiplied out form. That's just going to be -6 over 0. I would say, since that's undefined, we don't have a y-intercept. Our x-intercepts are the zeros of the numerator, and that's going to give me the 0.30 and -20. My vertical asymptotes are the zeros of the denominator, so it looks like x equals 0 and x equals -3, looking at the denominator factors. My horizontal asymptote comes from the quotient of the leading terms, that's x squared over x squared, or 1, giving me a horizontal asymptote of y equals 1. Labeling my axes x and y, I don't have a y-intercept to plot. I do have a couple of x-intercepts, 3, 0, and -20. A couple of vertical asymptotes, my y-axis, which would explain why there's no vertical intercept, and x equals -3. My horizontal asymptote is y equals 1. If I label it again, that will indicate my scale in this direction. Coming in from the left, I know I need to be close to the line y equals 1. It could be that I'm on top and it heads off to positive infinity at -3, or from the bottom heading down toward -infinity. I'm thinking, so I could do some test points, but just by process of elimination here, if I go down this way, I'm going to create an intercept here, and I don't have an intercept here. So just by ruling that out, I can tell I need this one for this part of my graph. Over here, well, I know I have to pass through the point -2, 0. I can ignore my horizontal asymptote in the middle. It's only giving me information about end behavior. What I don't know is if I come down from positive infinity or up from negative infinity, and then my next thing is the next vertical asymptote, and again, I don't know if I go down or up. So I might just test a couple of values. If I know that I get a positive value to the left here, I have to go up to positive infinity. I can't go up and then come back down. Again, it'll create too many intercepts. So maybe I'll try -2.5, and just -1 would be an easy one to calculate. And if I get those couple of points in there, I probably can determine what the behavior of this graph is. When I plug in -2.5, I get -2.2. When I plug in -1, I get a +2. So -1, 2 is a point on my graph. -2.5, -2.2, somewhere down here, as long as I know the sign of it, it looks like the graph has to do this in order to meet those vertical asymptotes correctly. On this side, well, I know that I need to get close to y = 1 on this end, and I need to pass through this point. But do I go down to negative infinity or up to positive infinity? Let's try one more value. How about plugging in 1? When I plug in 1, I get a -1.5, so that's down here somewhere. That means I've got to have this behavior. There's our graph of f of x. Right, so I'm using all the information that I'm given, and then just as needed, using some test values. If you need a lot more to convince yourself, feel free to do that, but I can see that it matches the behavior of both my vertical and horizontal asymptotes as well as all my intercepts. Let's try this one. I want to, again, find asymptotes and intercepts and sketch a graph. So let's start with a y-intercept as we've been doing. F of 0 is going to be 4/3. These are going to be 0. This is going to be 0. So 0 4/3. If you want to factor this, we may need that later. X-intercepts are the zeros of the numerator. So it looks like I've got two of them, -4, 0, and -1, 0. My vertical asymptotes are the zeros of the denominator, x = -3. My horizontal asymptote, well, ratio of leading terms. Do you remember this case? We had one in our, some pictures we were looking at that had an asymptote similar to this. There's no horizontal asymptote. There is, however, some interesting long-run behavior associated with this. Let me draw in some of what we have so far, and I want to talk about how we might think about end behavior even if we don't have a horizontal asymptote. Let me plot 0 4/3, so you just pick a spot to be 0 4/3. -4, 0. Again, I'm going to label all these to indicate my scale, and -1, 0. And a vertical asymptote here at x = -3. All right, let's just talk about our end behavior a little bit. This does have some consistent end behavior, just like the ratio of leading terms indicated. It's probably something linear. We got x when we did that. We can in fact find an exact equation for the linear end behavior, and we can do that by division. Let's divide, and I want to show you how we can use that to determine the long-run behavior. If we divide x times x, it's going to give me x squared. I'll subtract, bring down my 4. X times 2 gives me 2x. And once I subtract, I have a remainder of -2. So this is x plus 2 plus a -2 over x plus 3. If I want to think about the end behavior or horizontal asymptote or long-run behavior of this, I want to think about what happens to this expression. This is just another way to write the same equation, right? As x goes to infinity. As x gets bigger and bigger and bigger, This part, since x is in my denominator, this goes to 0. If I have a really huge denominator, well, negative 2 divided by something really, really huge is going to get tinier and tinier and tinier, both at positive and negative infinity, which means that my end behavior is actually going to start to match the linear equation y equals x plus 2. Okay, y equals x plus 2 has a special name. We know it wasn't a horizontal asymptote in this long run behavior. This is known as a slant asymptote. It's still a line, but with a slope other than 0. Let's see how the line y equals x plus 2 might help us. So we do have a slant asymptote, which is the equation y equals x plus 2. If I draw y equals x plus 2 in here, let's see. It has an intercept here and a slope of 1. So it looks something like this. All right, slope of positive 1 and y-intercept of 2. This is going to tell me about the end behavior of my rational function. So let's see. Coming in from the left, I know that my graph has to get really close to this slant asymptote. And then it has to pass through the point negative 4, 0. So I'm getting really close to this slanted line, just like I would a horizontal asymptote. I can plug in something like negative 3.5. When I do, I get something positive. So that will tell me that my graph continues up like this. So again, if I want some test points, or if I want to plug in something really close to negative 3 on the left, or just something like negative 3.5, I get a positive 2.5, so something positive. Moving right along in between here, well, it looks like I can ignore my slant asymptote in the middle, but I do need to match it at the end. I just need to figure out on this side, am I going to head down towards negative infinity or up to positive infinity? I can cross my slant asymptote. It doesn't matter what's going on in the middle. So maybe I'll plug in negative 2 and just see if that helps me see what's happening. If I plug in negative 2, I get out a negative 2. So negative 2 is a point on here. It looks like I'm going to head towards negative infinity. Again, if I had something positive, I'd know I want to head up here. I can't turn around and go back up because it would create an intercept that I don't have. I'm going to come up here and pass through 0, 4/3, and then as I head out this direction, get really close to my slant asymptote on this end. Here's a little summary about slant asymptotes. If the degree in the numerator is 1 more than the degree in the denominator, we can use long division. And when we do use long division, we'll get something linear. And the remainder heads off to 0. But this gives us the equation of the end behavior. It's the line y equals ax plus b, and we call that line a slant asymptote, or it's also sometimes called an oblique asymptote. Let's just look at slant asymptotes. Let's find the equation of the slant asymptote here. I know there is one because the degree of my denominator is 1 less, so when I divide, I'll get something linear. Let me put in my terms here that are missing, if you remember doing that. X squared times x is going to give me x cubed, so that's x cubed plus x squared minus x. When I subtract, that changes all my signs. That gives me negative x squared plus x plus 4, and this goes in here negative 1 times. I'm going to get a remainder. Sorry, I'm running out of room here. If I do the opposite sign here, I'm going to get 2x plus 3 for my remainder. This, as x goes to infinity, heads off towards 0. That's always going to happen with that remainder. What's left tells me that my slant asymptote is y equals that line. Just like with horizontal asymptotes, I want to make sure I give the equation of a line, not just x minus 1, but y equals x minus 1. That's my slant asymptote. This is all the graphing I'm going to do in this video, but do note that in the modules I have a link to a bunch of other video examples, and there are lots of examples to check out there. So if you want to see more, please refer to that. I do want to do one application before we're done. C of T is the concentration in milligrams per liter of a drug in the bloodstream T minutes after an injection. And here's an equation for C of T. It is a rational function. Let's just find the horizontal asymptote and explain its meaning. So the horizontal asymptote, I want to look at the ratio of leading terms. This is equivalent to 30 over t, which as t gets large goes to 0. That means that our horizontal asymptote is y equals 0, or in this case, c equals 0. What does this mean? Well, a horizontal asymptote tells us what's happening at the ends, and in particular, since t is time, this makes most sense for t getting larger and larger. As t goes towards infinity, or as time passes, the concentration of drug in the bloodstream tends towards 0, and that totally makes sense. If you give an injection, the amount in the bloodstream goes down over time and tends towards 0. So I'll just say here, as time passes, the amount of drug in the system or in the bloodstream gets closer to 0 milligrams per liter.